Hello everyone, and welcome back to another Eng 130 video tutorial. In this tutorial, we're going to cover a new concept with trusses called the method of sections. So as you guys remember before, in the previous two videos, we did the method of joints. And what that is instead of analyzing kind of the truss as a whole, we break it into a part at each joint. And what happens is all the members at that joint turns into a force. Now, this method is really good if we have a nice small truss. However, in reality, very rarely will we have a small truss. Usually trusses are used to span large distances, so they usually have a lot of members. So if you guys want to use the method of joints, it's perfectly valid. It'll take you a long time. And what you guys will usually see in the final is that the truss, it'll be not complex, but it'll have a lot of members. And because of that, it can actually be really tedious to go through each one of the joints to find all the forces in the members. So what there is there's actually a second method that we're going to use called the method of sections. And what this method involves is kind of a simplified way to find a bunch of forces inside the middle of a truss without having to analyze each one of the joints. And what's kind of nice for us is it uses the same principles as the method of joints. And that principle being specifically is that when we analyze a joint, we want to create a free body diagram of that joint. So what we do is we cut all of the members around that joint. Well, what you're going to see in the method of sections, we're going to do the same thing. We're going to cut the truss. And what happens is wherever we cut on the truss, whatever members we cut through, we replace those members with forces. And then what happens is you can actually get a nice free body diagram with a bunch of forces based on the members that you cut. So if we're only interested in, say, 3 members, what we can do is actually cut those members, turn them into forces, and then solve for them just using our 3 equilibrium equations. So this should be a nice, kind of hopefully simple tutorial. The method of sections, even though it sounds a little bit scarier, is actually, in my opinion, the easier of the two because it's very straightforward. And there's some tricks with this, as you guys will see, that you can carry into the final. Let's begin. Alrighty, so looking at this example, it wants us to determine the force in members DC, HC, and HI of the truss. And then, of course, state if the members are in tension or compression. So again, in my opinion, even though a question may not ask for this, you should do it. I believe in the final, if they ask for it and you don't put tension or compression, you will lose marks because that's kind of the trick to trusses is otherwise they're just a bunch of cables if we want to find the forces. It's very important if we know what's in tension or compression because, like I said earlier, the design of tension member is a little bit different than the design of a compression member. So that's kind of a good thing to know. So with the method of sections, the best thing for you guys to do when you guys are given a question like this and it asks for very specific members, it's usually going to be the method of sections because these members, I guarantee, are not going to be near a support. If they're near a support, then we can actually go back to the method of joints and find them very easily because we won't have to go very far into the truss to solve for the forces. However, what I like to do for these questions is I'm going to highlight the members it wants us to find. So the first one's DC, which is right in the middle of the truss. So that should be kind of your first hint that, hey, we're going to have to cut this truss using the method of sections. The second one is HC. So if we look, this one comes right across here. And then our final one is HI, which comes down here. So this is kind of what you guys will usually see. It wants a couple members, and what you guys will find with the members is they're usually very close together. So now we're going to discuss the method of sections. So the method of sections is basically if I want a bunch of members in the middle of the truss, and for fun, let's just say it's these members right here, ED, EH, and GH. Well, what I can do is I can literally cut the truss right down the center. So let's say I cut right here. And I can draw a free body diagram of any side of that cut. So what I'm going to do on this side, if I were to look at this and say, okay, if I made that cut in the red line, well, there's a lot less going on the left side. So let's analyze the left side. And what I would do is I would draw a free body diagram based on the side I want to analyze. And what you're going to do is you're only going to draw forces on the members that you cut. So if I'm starting at point F, let's just say right here, well, I know that there's a member from F to G. So that goes from F to G. So this would be point G right here. I know that there's a member EG, which goes up like this. Oops, let's not draw it super tall. Actually, I think I messed up. All right, let's draw it up to, oop, that's too much. because I got a force on there. So let's say that this is EG. So again, I didn't cut through these members, so I'm not putting them as forces. They're just kind of beams, if you will. I got member FE, so from here to here, again, this one wasn't cut. So this is not a force. And that's it for the members that I didn't cut. Now, we also have reaction forces and external loads. So we know that at point E, right here, we have 40 kilonewtons coming down. So we have to include this because it's on the side that we're going to analyze. So this would be 40 kilonewtons. And then if we look at F, we actually have a roller right here. So we know that there's going to be some sort of roller, which will be, I'm just going to call it Fy. So before we even start analyzing the member forces, one of the things I told you guys we're going to have to usually do is find the support conditions. And in this case, if we want to analyze this, we're going to need that support condition, because without Fy, as you guys will see, we won't be able to solve for any of the forces. Now, this is kind of the tricky part, the part that hopefully you guys will understand, and that is we cut through some members. So if we look at joint G, way at the bottom, right down here, we cut through member GH, so we can see the cut going through GH. So all we're going to do is replace that member with a force. And again, we're always going to assume it's in tension. So I put this as a force, and this will be member GH. If I look up at joint E, kind of at the top, we cut through two members. We cut through ED, which is going horizontal. So I'm going to put this as a force ED, like this. And then I'll have another force kind of going diagonal, because I also cut through this one. And this one right here is EH. So if I were looking at this, and remember, the first step in this is always to solve for your support condition. So I will already know Fy at this point. If I look at this, I have 1, 2, 3 unknowns. And remember that we also have 3 equilibrium equations. Sum of the forces in X equals 0, sum of the forces in Y equals 0, and sum of the moments about any point is equal to 0. So 3 equations, I have 3 unknowns. I would actually be able to solve for this. For instance, if I was given this scenario and I were to do sum of the moments about point E, so this point right here equals 0, well, we know that both ED and EH will not create a moment because they both pass through that point, but GH will. So GH will create a moment and Fy will create a moment. So from this equation, our only unknown is GH. We can solve for it. Moving on, I can do sum of the forces in Y is equal to 0. Well, if I look at that, both ED and GH are horizontal forces, so they won't be in this equation. However, EH will be. So I can solve for EH. And then finally, if I already know GH and EH, well, then I can do any equation I want, but in this case, I'm going to go sum of the forces in X equals 0. And as you'll see, we would have components of all 3 of those forces, but since we already know 2 of them, we can solve for the third one, which is going to be ED. So as you guys can see, if we cut through members, we can use simple equilibrium to quickly find all those forces, which is really, really nice, because if I were to go right to point E, so where this purple is, and do the method of joints, so I come down here and say, okay, well, let's say instead of the method of sections, I'm going to stick to the method of joints, and this is joint E. I would have ED, so there's 1. I would still have EH, so this is okay because those are 2 that we want, so that's not too bad. But now things are going to start getting messy because we also have EG coming down. And then if we look to the side, we have EF. So just by this joint alone, we're having a lot of unknowns. EF, and then we have EG. And then we also have external force here, but that's okay because we know the external force, so that's not going to give us too much trouble. But the fact that we have all those 4 unknowns, we can't solve anything in this equation. So what we'd have to do, if we were doing the method of joints, is we'd have to analyze joint F to give us these 2. We'd have to analyze joint G to give us these 2, and then we can analyze joint E to give us these 2. But that's a lot of work. You guys don't want to do that, especially in a final. You guys have already wrote the midterm. You guys finally know what I mean by it's a time crunch. You guys have been through that time crunch now. You guys are very aware of it. So we're going to try and do these tricks to save us a bunch of time. And that's what we're going to do with the method of sections. Now, the method of sections, I'm going to start erasing this because we're only going to focus on the ones that we want. The hardest part that you guys will have for the method of sections is determining where do I cut. Because remember, you can cut anywhere along this beam as long as you replace all the members you cut with forces. If I wanted to, I can cut like this. That's perfectly fine. And if I was analyzing this intersection, well, I would have a force here. I'd have a force coming up. I would have a force coming to this side. I'd have a force coming down, force coming diagonal, and another force coming down. So in that case, I'd have 6 unknowns. That's probably not a good cut. Because remember, we only have 3 equations. So if we have more unknowns than equations, then we're not really getting anywhere. We're just creating problems for ourselves. So what you're going to want to do kind of as a rule of thumb, and this is not all the time because there's very special tricks that you guys can do to solve for things a little bit easier if you cut through more than 3 members. But the little trick that I like to do is highlight the members that you want to cut. And that's why I highlighted those 3 members. Because as weird as this may sound, usually in the final, if you highlight those members, it'll show you your cut. So what I do is I highlight the members, like you guys see, and then I cut through all those members. So this will be my cut right here. And if I look through that, I cut through 1, 2, 3 members. Well, that's great. I have 3 equilibrium equations, 3 unknowns. I should be able to solve for everything. Now, if I look, I can do this in one of 2 ways. I can analyze this side over here, and that's perfectly fine. Or if I want, I can analyze this side down here. And both are completely valid, so it's completely up to you. But one thing, and this is the reason why I'm showing you this, if I look at the top side, I have a roller. If I look at the bottom side, I have a pin. So no matter what side you pick for this example, and for most of the examples when it comes to this, you're going to have to find support conditions, which is usually the first step in all these things is to find the support conditions. So I'm just going to erase this real quick. So what I'm going to do is I'm actually going to analyze the bottom side because I'm just showing you guys we can analyze whatever side we want. So this is going to be the side that I analyze. But before we do that, we need to find support conditions. So I'm going to go down here, and the first step that you guys should do in your exam, don't use a highlighter, trust me, that won't work out well, is you're going to want to find support conditions. And the best way to do that, well, just using what you guys already know. Remember, week 6, I warned you guys. I said this week, it's really, really easy. It's not supposed to be very hard, but it's very important that you understand support conditions because you guys are going to use them basically until the end. So what I'm going to do is I'm going to start drawing the truss. Because to find support conditions, the best thing you guys have to do, draw a free body diagram. So if I were to draw this truss, I know that I got kind of 3 like this. I'm not going to draw it perfectly to scale. Remember, you don't have to draw it to scale as long as it looks reasonable. Like if it looks terrible, then yeah, you're probably not going to get full marks. But I'm sure that you guys can draw it more reasonable than I ever can. So I'm just going to draw the truss as a bunch of sticks. Nothing special. And the best way to find support conditions, I guess I should throw this in there, even though I've told you guys this before. Treat the truss as a whole. Don't try and cut the truss and then find support conditions. You should always be able to find the support conditions as a whole. They would be really, really mean to make it so that you have to cut the truss to find support conditions. So there's my truss. I'm going to put some external loads on it. So we know at the top here, we got an external load here and an external load here. So if you guys want, you guys can just pause the video up top to keep track of all the external forces because this truss actually has quite a bit of them. So we got 40 kilonewtons at the top. We got 50 kilonewtons at this side. If we look up top, we got some lateral loads on the right-hand side. So we got the 30 and the 40. It's coming down here. We know we got some lateral loads like this of 30 and 40. Put arrows to show the direction. So we got 30 kilonewtons. We got 40 kilonewtons. And now that's it for external loads, but we have to keep in mind our our support conditions. So at the base at A, we have a pin. So we know that this is actually going to be two forces. We're going to have a horizontal force and a vertical force. So here's my vertical force, AY. We're going to have a horizontal force, AX. And then at F on the other side, we have a roller. So we're just going to have a vertical force for that, which I'm going to call Fy. And that's all my forces. Now, this is not a complete free body diagram because we're going to also need to throw in dimensions. So we know that we kind of have 3 spans going horizontally. So each one of these will be a 2-meter span. 2 meters. And then we also have 3 spans going vertically. So like this. So we look at this, what we have is these are each at 1.5 meters. 1.5 meters, 1.5 meters. So now looking at this free body diagram, we have all our forces, we have all our dimensions, we can start going ahead and solving everything. So the first thing I'm going to do is I'm going to take the moments at the pin. So the sum of the moments at A is equal to 0. So if I'm doing this equation, we're going to go through and check, okay, well, AX and AY, they hit point A, so I'm going to actually just put this as point A right here so you guys can all see. And then we also see that the 50 kilonewtons run straight down into A, so that will also not create any sort of moment. So starting at the left and working my way over, I know that Fy is at a distance, so I'm going to go Fy times its distance to A, which is 4 meters, so Fy times 4. And now we got to check direction. So if I were to hold my pencil at A and push up on it like Fy does, as we're going to see, it's going to create a negative moment because it's going to go clockwise. So this is going to be negative. Moving on over, we know that the 40 kilonewtons will also create a moment. So we're going to have 40, and it acts at a distance of 2 meters. If I hold my pencil at A and push down on the left side of it, we're going to see it's going to start rotating counterclockwise, so this is actually going to be a positive moment. So we're going to have plus 40. Now we deal with the 2 lateral loads, so let's start with the 30 kilonewtons. So we got 30, and it acts at a distance of 3 meters. And if I hold my pencil at A vertically and push to the left on it, as I'm going to see, it's going to start rotating counterclockwise. So it's going to be positive. And then at the bottom, it's going to be the same direction for moments. So we're going to have 40 times the 1.5 meters. And all of this is in equilibrium, so everything must equal 0. So from here, we can move Fy to the other side. And what we find out is that Fy is going to be equal to 57.5 kilonewtons. And the direction of that is assumed correctly, so we know that it's up because we had a positive answer. Therefore, our assumed direction is correct. So there's the first one. I'm not highlighting anything. This isn't an answer. This is just a support reaction. Remember, our answers are going to be those internal forces in the truss. So now that we know Fy, we can do sum of the forces in X, sum of the forces in Y to find the rest. So if I go sum of the forces in X is equal to 0, well, this is actually going to be kind of the nicest one because we know we have AX going to the right, and then we have a lateral load of 30 going to the left, and another lateral load of 40 also going to the left, but that's it. So that's equal to 0. We find that AX is equal to 70 kilonewtons, and it's a positive answer, so our direction of going to the right is correct. So we're just going to put a little arrow to remind ourselves that direction is correct. And finally, we can wrap it up with sum of the forces in Y is equal to 0. And again, this is going to be a nice easier one. So if we look at our diagram and looking from the left and then move to the right, well, we got Fy going up. But we already know that Fy is 57.5. Coming up, back up to the diagram, we have 2 downward vertical loads of 40 and 50. So these will both be negative since they're downwards. So minus 40 and then minus 50. And if we look up at the diagram, we have an AY assumed going upwards. So we're going to go plus AY is equal to 0. And when we solve this, we get AY is equal to 32.5 kilonewtons. And it was a positive answer, so we know that our assumed direction of up is also correct. So now we have our support reactions. Now we can go into the fun part, which is cutting the beam. So we've already discussed about it, but the best way to cut the beam is to highlight the members you need, cut it, and then you're good to go. So this is our cut. We're going to cut it at the red line. So what I like to do too, just to help distinguish if you need more than one cut, is I just go 1, 1. And then when I come down here, I'm going to say cut the truss at line 1, 1. So cut truss along line 1, 1. So that means that we're cutting the truss along that line. You guys will have to show your cut when you guys go into the final. So make sure that your cut is kind of nice and clear. And then we can analyze, like I said, we can analyze that top half or the bottom half. We're going to pick the bottom half. But what you're going to have to do after your cut is make another free body diagram. So we're going to go down here and we're going to make a free body diagram. And the first thing that we're going to want to do is let's just throw in all the members that we did not cut. So we know if this is point A down at the bottom right here, we had a member AI. So this is going to go up like this. So that's point A. This is point I. We didn't cut them. We also know that this comes across to point B, and we didn't cut B either. So I'm going to put this as B. Actually, I'm going to not put it there because we have a load there. And we didn't cut AB, so these forces are still good to go. BC, we also didn't cut. And then there's a member going across, which is IC or CI, that we didn't cut. So these are the members that we didn't cut. So if I'm looking at the diagram to show you those, and I'm going to highlight them in dark green, those will be these members right here. We didn't cut them, so they just remain members. And did I get the one going across? Oh, I did. Perfect. So now I'm going to want to put in my support reactions that I already found at point A. So I'm going to switch to a red color just to show that these are my support reactions. So we know that we had an AY going up like this, and then we had an AX coming across like this. And we know their values, so I'm just going to put them in directly. So this is 32.5 kilonewtons, and AY is 70 kilonewtons. We also know that we had some lateral loads acting on these two joints, so we're going to throw those in too because those will be very, very important. So the one at the top is 30 kilonewtons, and the one at the bottom is 40 kilonewtons. So now is kind of the fun part, is now we need to add in the members that we cut. So if we look over here, we see that we cut through HI, and that's a vertical member. So I'm talking about, I probably shouldn't do it in purple, let's do it in dark blue. HI, which is this one right here, we cut through. So we have to replace that one with a vertical force. So we're going to have a force like this, which is going to be HI. If we look up top some more, we have a horizontal member we cut through right here, which is CH. So right here, I'm going to have member like this. And this one's going to be CH. Actually, I'm going to put that at the bottom just because to save some room later on. I don't want to get in trouble. And then finally, if I look up to the top, I cut through a diagonal member CD right there. So I'm going to also have to throw in CD, which is going to be something like this. So CD. Alrighty. So free body diagram's almost complete. So one of the other things that you have to make sure that you remember to do is just dimension it. So we know that we have two spans now going this way, and each of them are still going to be 1.5 meters. 1.5 meters. We have a horizontal span like this of 2 meters. 2 meters here. And then one other thing that we should also do too is we have a diagonal force, so we should put in its geometry. But we also know that this is very easy, that it goes up by 1.5 and its horizontal span is 2. So this right here would be a pretty good free body diagram. One thing I recommend putting in, but I don't really know if it's a must, is just the point names. So we got A there, and if we look up to the top, it goes B, C, I. So we know that this is going to be point B, C, I. Because if we're going to take a moment anywhere, we should tell the marker where we took the moment about. So for instance, if I were to take the moment about C, and I didn't label that as C, you'll probably get a mark off because you're taking the moment about a point that we don't know what it is. You have to be very, very clear where your points are. So if I'm looking at this, I have a free body diagram, it's good to go. I have 3 equations, and if I look here, I have 3 unknowns. So this works out actually very, very well. So now I can start going through and solving these forces. And the nice thing about trusses is there's actually a lot of way to solve for these very, very quickly. But I'm just going to go with whatever I think is obvious, and then I'll show you some kind of tricks at the end to solve for some of these forces. Because there's kind of one big one with trusses, as you guys will see, and you guys are going to hate it. Like, it's not a nice thing because it requires thinking outside the box. And that's something students don't like to hear. They prefer kind of a more straightforward approach. So they don't like hearing that they're going to have to think really hard. But the first one I see is taking the moment at point C. Because if I do that, it'll get rid of CD and CH, which is perfect. That's exactly what I want. I don't want to deal with those. Let's get rid of them. So if I go sum of the moments at point C is equal to 0. Well, if I look here, CD doesn't create a moment, CH won't, and also that 30 kilonewtons also runs through there, so we know that also won't create a moment. So we're going to have to consider all the other forces. So looking kind of left to right, I see that HI will create a moment. So we got HI, and we know that that one acts at a distance of 2 meters. And if we look, we're going to see that that's going to create a negative moment, so negative HI times 2. We see that the 40 will also create a moment, so we got the 40. It acts at a distance of 1.5 meters. And if we look at this one will also create a negative moment. And then we have to look at the conditions at A. So both of those support conditions will create a moment at C. So let's start with the vertical one. We got 32.5. And we know that this one acts at a distance of 2 meters. And this one will also create a negative moment. So a lot of negative moments happening right now. And then finally, we got the 70 kilonewtons. So we're going to have 70. And it acts at a distance of 3 meters. And we see that this 70 will actually create a positive moment. So it's kind of nice to see some positive moments in there. And we know that this is all in equilibrium because of statics. If it's not in equilibrium, then you guys should just not do the question, because that's not what this course is about. So what you guys will get is you guys will get that HI, so this is the first one that we want, is equal to 42.5 kilonewtons. And what you'll see is this is a positive answer, and just like the method of joints, we always assume tension. So if we get a positive answer, this means that this is in tension. So what we can do is we can highlight this answer. We're good to go. Perfect. So we can move on. If I were to look at this truss now, okay, well, if I take some of the forces in X, I got CD and CH in there, and I don't know either one of them, so that's not a good idea. But if I look at some of the forces in Y now, I got HI and CD, and I now know HI, so I can actually solve in that equation. So if I'm doing sum of the forces in Y is equal to 0, well, then I look up, I got AY at the bottom, which is that 32.5. So I'm just going to come down here, and I got 32.5 going upwards. I look up, well, I got a lot of lateral loads, so those won't create anything. I got HI going upwards, so I go plus HI, and we already know that HI is 42.5, so plus 42.5. And if I look up, we also have CD, or actually I'm going to put this as equals to DC, because I think that's how they put it in the question. Usually I put the first letter first, but again, they're the same thing. It doesn't matter. So we're going to have plus DC because it's going upwards. However, we see that DC is at a diagonal, so we only want one component. So we know that the hypotenuse here is going to be 6.25. So the vertical component is going to be 1.5 divided by the square root of 6.25. And all of this is equal to 0. Because again, it's in equilibrium. We're not going to disturb that. And what happens is we get DC is equal to 125 kilonewtons. But what we'll see is the answer that we get if we do this formula is DC is actually negative 125. So what that means is it's assumed tension is wrong. 125 is actually in compression. So we're going to still have it as 125 kilonewtons, but we're going to specifically state that this member is in compression. So there's the second force. And if you guys get past the second force, you guys are laughing because only one unknown. Pick whatever equation you want. So I'm just going to come down and I'm going to do sum of the forces in X is equal to 0. And there's a lot of lateral loads in this one, so this one will be quite a longer equation. Starting at the bottom, I see that I got 70 kilonewtons going to the right. So we got 70 to the right. And then I got 40 and 30 going to the left, so minus 30 minus 40. So this is kind of a funny scenario where AX actually cancels out with the two lateral loads. I see that I got CH going directly to the left, so we're going to have minus CH, but I'm going to put it as HC because that's how they put it in the question. But again, they're the exact same thing. It doesn't matter. And then we also see that we got DC going to the left, or at least a component of it. So we're going to go minus DC, but we want just the component, which is going to be 2 over the root of 6.25. And we know that all this is equal to 0. So we know that DC right here, well, we know it's 125, but since it's negative, we have to include the negative 125. So now we know that our only unknown in here is going to be HC. We can solve, and what we get is HC is equal to 100 kilonewtons, and it's a positive answer, so our assumed direction of tension is actually correct. So I'm going to just put a box around this because it's good to go. And those are our three forces. So now, if you guys look up and compare, we solved for a bunch of forces in the middle of the truss without even touching the method of sections. The method of joints. If I were to analyze those forces, so I'm going to just kind of erase some of the crap real quick. So if I wanted to analyze those, so I'm going to highlight them in purple. So these were the members that I wanted. So it'd be HI, DC, and HC. So this one across here. If I were to do the method of joints, I would have to analyze at least up to this joint, or this joint, or this joint, or this joint. So to get to those, I'd have to at least do 2 extra joints. Or if I were to go from the left side, there'd be a lot of extra joints. So this is clearly the better option when the forces, the members are in the middle of the truss. And like I said, don't worry about it too much because it's usually pretty obvious where the cut will be. If you highlight the members, just cut through those members. 90% of the time, you're good to go. The other percent of the time, get a little tricky. And then the other thing I wanted to show you guys real quick is the kind of the sneaky thing that a lot of people like to do. Or a lot of professors usually like to do this. And that is taking the moments. So this question was very, very nice because we knew to take the moment on the truss, we got rid of 2, and then we can find the rest. Basically, we took the sum of the moments on the truss. However, there's a lot of cases where it's not obvious where to take the moments about. And actually, it's better to take the moments on a point that's not on the truss. Well, Clayton, hold up. That's not on the truss? Exactly. A point that's not on the truss. Let's say that before I started taking any moments, and I was just looking at this diagram right here, so let's zoom in. Maybe not that much. Zoom into here, and I wanted CD first, or DC. So let's say that for fun, this is what I wanted first. And of course, I was going to say, okay, well, if I take the moment at I, I'm still going to have CH and CD, so that doesn't work. However, you can take the moment anywhere you want. And that's kind of the trick to these truss questions. Sometimes. Sometimes if they're mean. So, for example, I can take the moment at this point. Actually, I'm going to do it in a different color to really make it stand out. Do it in pink. I can take the moment at this point right here. It's off the truss. And this is actually a point on the truss. So if I look up, this is actually this point H right here. So if I come down here, this is actually point H. And it's not on my method right now. It's not on my cut. But if I look here, HI will hit H. CH will hit H. So they both won't create a moment. And I can solve for CD or DC directly. So that's kind of one of the tricks, is realizing where to take the moment about. And then you have to remember, you don't always have to take the moment on your free body diagram. You can take it off the free body diagram, save some time. So I think that's it for this tutorial. We'll do another one with the method of sections. And then I have an additional video kind of at the end that'll show you kind of all the tricks. So we're going to go over all like the little tricks to kind of make the questions easier. And namely, that is something called zero force members. But I'll kind of save that for another day. You guys will see it, get really excited. So thank you guys all so much for listening. I'll see you guys in the next video.